Here we're going to talk about the moment of a force, but we're going to now talk about it in terms of its vector formulation as a cross product. I've hinted for a long time now that all of these calculations we've been doing to find the moment is really, in the grander scheme, it's really a cross product. So that's why we covered all of that before. So to get you comfortable with this idea, let's just recall some things that we had talked about in the previous set of lessons here about moments. So I'll draw a quick picture here. What if we have, let me go ahead and change to red to draw the coordinate system. What if we had a vector, well, let's do it like this. Let's say here is, here's the z direction, here's the x direction, and then over this way is the y direction. So here is, of course, z. Okay, so now let's say that I have a force, or I should say a force acting at some point here. So let's say the distance from the origin, okay, is called r, and that's a vector, and here's the origin. So here's some big point here at the center of the universe or whatever. We construct some coordinate system. All right, now let's say that acting at this point, you can imagine r to be a piece of wood or something, or if it helps you to visualize it as a piece of wood or a piece of metal or something. And then acting at this point, more or less in this direction, is some force. Okay, acting right at that point, and that's some force F, and of course it's acting at some angle theta to the vector r. So this angle theta in general could be any angle at all. So what it basically is saying is, if you're trying to figure out how an arbitrary force is going to cause a moment about some axis of rotation that's denoted there, then what you need to know is three things. You need to know what is the force vector, its direction and magnitude, that's given by the arrow. And you need to know what the angle is between that and the distance vector from where I'm trying to rotate to, which is governed by this guy. Now we've said before that you already know if this is a piece of metal here and I'm directing a force like this, then it's going to tend to spin the thing around. And we know from the right-hand rule that if we curl our hands in the direction that this is going to attempt to rotate r, if you kind of consider F to be in the plane, in the xy plane here, then this thing's going to spin like this, and from the right-hand rule, the moment is going to be oriented straight up. So the way that we typically write that is we say that the moment vector is oriented up like this, and it's basically spinning in this direction, and we call that m0, or m sub o, and it's a vector as well. So the actual moment vector, notice, is oriented perpendicular to the plane that contains these two vectors here. So this is like a sheet of paper. The r vector and the f vector that's pushing on it, they're in this plane here. The moment actually comes out of the page like that, and I've drawn an arrow to signify the thing is rotating like this. Now this is all more or less review, stuff that you should have remembered from before, but just go a step further. Remember that the moment about the origin here that we're talking about here, or at least the magnitude of it, if you remember, it's going to be F times d, right? But we've said many times that it's not just F, it's the component of F perpendicular to the moment arm that we've been talking about this whole entire time, right? We've done that enough times. So basically it's the distance here from here to this point where the force is applied, okay? And then we have to take into account that there's some angle here, right? So what we say is F times the sine of theta, okay? And this F sine theta is perpendicular, it's F perpendicular to R. So if you kind of think about it, I know it's a little bit hard to see in this drawing here, but basically what we want to do is we want to figure out how much of this force is acting perpendicular straight on to the r vector there. So we take this guy, we take the sine of it, and I know it's drawn a little bit into or out of the board, but again, think of it in 3 dimensions here. This guy is angled at some angle to r. We want to figure out how much is pushing straight on r, and so that would be this component more or less going in like that, sine of theta, F times sine of theta, okay? Now, that is if you're going to think about it in terms of a perpendicular component of the force. However, you could also say that this could be equal to r sine theta times F, whereas this is r perpendicular to F. So in other words, there's 2 ways to think about it. I've been harping on them over and over again. One way is to take the r vector from the origin to the point of application and then multiply that by the perpendicular component of the force. That's what this is. Or you can think of it as saying, I'm going to take the perpendicular distance from the origin. Notice this would be like a perpendicular distance. And notice from geometry, r times the sine of this angle is going to give you this perpendicular distance that intersects the action line of my vector here. So that's this times the full-blown force. But notice that when you do these computations, either way, you get the same answer. R f sine theta, R f sine theta, they're giving you exactly the same thing. It's just one way you think of it as perpendicular force acting on R. The other way you can think of it as perpendicular R going to the line of action of your force. Okay, this is honestly stuff that we've already discussed in the past, but it's very appropriate for what we're talking about here because this calculation is a scalar calculation. It's just basically giving me the magnitude of the moment, and the direction we always know is perpendicular to both of these two vectors. But in reality, I'll just write it exactly like that. In reality, the moment about point O is really a cross product of R crossed with the F vector. And this is really the most important thing that we're going to talk about in this lesson here. This, there's a joke in electrical engineering that you can solve every problem with Ohm's law. V is equal to IR. Okay? If you know that, then you can solve anything. And it's a joke because, of course, problems get difficult and you can't quite say that that's exactly true, but certainly Ohm's law is fundamental. Right? Well, there's another joke that in mechanics you can solve almost every problem with R cross F because that's giving you the moment of a force about some axis of rotation. And really every single problem we're going to work from here on out is really just messing around with these moments and the forces that we're dealing with. So the turning actions and the force actions that coming from different angles there. And so we're going to be looking at equilibrium problems all the time when we're looking at the sum of all of these moments here. But what we have in this particular case is you have the R vector and you have the F vector, and we're saying that the moment here is actually the cross product of R crossed with F. Now to prove that to you, okay, let's take the magnitude of this. What would be the magnitude of the moment that we get? See, this is a vector here. I should put this guy here. What would be the magnitude? Remember, the magnitude of any cross product is equal to the magnitude of R times the magnitude of F times the sine of the angle between them. Does this look familiar? It's exactly what we've been writing here. RF sine theta, RF sine theta, RF sine theta. Because the moment is defined as a cross product, and because the magnitude of a cross product is magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them, the cross product, when you take the magnitude, it's exactly giving you all of these problems, everything that we've been talking about before. I just never called it a cross product because I wanted to start in 2 dimensions to show you how to build up to it. But now we'll have vectors pointed arbitrarily. It's going to be difficult to find components in different dimensions and then find the perpendicular parts of it. So all you really have to do is take the R vector, the distance from where I'm rotating, the F vector, which is the actual force, which encompasses the direction of the force, in the direction of R, cross them together, and you're going to get a vector. The magnitude of this vector is going to be given by RF sine theta, and the direction of this vector is perpendicular to R and F. Why is it perpendicular to R and F? Because when you look at the cross product, when I talked in the cross product in the last section, when you have two vectors, when you have any two vectors, you can always define a plane that contains those two vectors. Any two that you pick. This one and this one, there's a plane right here. This one and this one, there's a plane right here. When you cross two vectors, your thumb is always going to point perpendicular to both of those vectors, to the plane containing them. So the direction of the moment that you get is always going to be perpendicular to the two vectors you started with. So I'm just trying to prove to you that when you say the moment is R cross F, it's everything is consistent with everything we've been doing. It's just in the previous problems we had two-dimensional problems. All of the moments were coming out of the board or into the board because all of the forces and the moment arms they were all in the plane of the board for all of these other problems. So if we take a look at this particular problem again, how would we calculate R cross F? Well, whenever you're doing mental gymnastics with R cross F, you need to, the way I've drawn it here is how you would have constructed it. You'd put a pipe here, and you put a force at an angle at the end of the pipe. But to actually calculate the cross product, you need to shift the vector over and put it tail to tail. Okay? So the way that you would do that, is something like the following. So basically, you would have here we have here, this is R, this was F from before, just like this. Okay, and if you're going to actually cross these guys here, you can move this vector around, and notice you have to keep the orientation the same, and then you can move it. There's many ways you can do it. You can move it back over here to the origin and put them tail to tail, like this. Or if you wanted to, you could just you can shift the guy up here and shift R over here. Like you could, let me switch colors to red over here. If I wanted to do it here, I could shift this vector here. This would be the F vector. And this R vector I could shift over here. R vector like this. See, either way, what's going to happen is, if I take F and I move it here, this is tail to tail. If I take F and move it here and take R and move it here, this is tail to tail. Either way, when you do a cross product, you want the vectors to be tail to tail. So I'll write that down, tail to tail, when you cross product, when you make the cross product of these things. And the reason that's important is because now whenever I cross R, and you got to kind of visualize that these are kind of laying in the plane here. I know I haven't drawn it perfectly, but when I cross R into F, I want to cross R into F, first going into R and then cutting into F. Here I'm doing the same thing, cutting R into F. And so then my moment is going to be exactly as we've drawn it over here. It's going to be something like this. And again, I know this isn't totally awesome because of the way I've drawn it, but really these angles would look a little better if I drew them a little bit shallower so that you can kind of visualize them being in there. And if it helps you, you can kind of visualize this being almost like in one plane here. So you can kind of visualize it as a sheet of paper here. And what you have here is you have R, you have F coming in at an angle. This angle is the same angle that we have right here or right here. These are all the same angles. So to actually find the cross product graphically, you can shift this up and over and do it, or you can shift this tail to tail and do it. But either way, no matter what you're doing, you're getting a cross product that shows the direction of the guy and you're showing its rotation. Okay, now we already talked many times before about the concept of if we have a positive moment, meaning a counterclockwise rotation, we're going to consider that positive, and then we have a negative moment, we're going to consider that clockwise rotation. That's really appropriate and very useful for two-dimensional problems when we have either left-hand or right-hand rotations. In three-dimensional problems, you can literally have rotations in any direction, so really it's much easier because if you're going to add moments together, you just basically take the vectors that come about and you just add them up. The algebra takes care of the direction. And so then when you want to find exactly which way the thing is rotating, you just look and see which direction is this moment pointing and you curl your fingers around it. So anytime you see a moment oriented as an arrow, curl your fingers around it. That is how the thing is rotating, like this in this case. Curling your fingers this way means a rotation like this, which is exactly what would happen if I pushed on this piece of metal or whatever it is I had here. All right, a couple more things we want to talk about. I want to talk about them right under here. And this was a really good introduction, but we also want to talk about something called the principle of transmissibility. Right? Now, I was tempted, I wasn't really even sure. Should I cover this? Should I not cover it? Because it's kind of obvious, but it's not 100% obvious if you've never studied mechanics before. It's something every book will talk about, but it might be buried in a paragraph. It might not bring it out to the forefront. I want to bring it out to the forefront so that you're not confused when you're solving your problems. What I want to do is write down what is the principle of transmissibility in words, and then I want to draw a picture. So what I'm basically saying is that force vector F can act at any point along its line of action and produce the same moment about some axis of rotation. We'll call it O. So let me read that again and we'll draw a picture. The principle of transmissibility, it's very important because when you are solving problems, you can take advantage of this principle here to make your calculations easier. It's basically saying that force vectors, in this case F we're calling it, they can act at any point along their line of action. Remember, what is a line of action? It means that if I have a vector here pointed up in this direction, or a vector pointed back like I'm pulling on a rope, then the line of action is basically just going on positive and negative directions on either side of that line there. The line of action literally is a dotted line that extends in front of your force and behind your force. So what it's saying is force vectors can act at any point along their line of action and produce the same moment about the origin. Let me explain how this works, and actually it comes about because of the way the cross product works. It's not a magical statistics thing or mechanics thing. It's something that comes about because of the way the cross product functions mathematically. And it makes 100% sense. So let's draw a quick picture, for instance. Let's say that I'm looking down, so I'll say looking down. So this is like an XY plane down here. And let's say that I have some center of the universe that I care about, O, okay? And let's say that over here I have some force. Actually, let me draw, we'll call it R2. You'll understand why I'm calling it R2 in just a second. All right, and at the tip of R2, now you can think of this as being a rigid beam or just something to connect the origin to some point over here, right? And then at the tip of this guy here, I'm going to apply a force going straight up, and I'm going to call this force F, just like this. Now, let me ask you a question. What moment is this thing causing about an axis of rotation that goes through O like this? Well, the way I've drawn it, this is horizontal, this is vertical, so this is 90 degrees. So you should know by now that the moment is R times F, right? That's the magnitude of the moment, right? And the direction is going to be a rotation that goes, notice that this force is going to attempt to rotate this thing like this, which is counterclockwise, which is a positive sense. So it's going to rotate it, and the moment vector is going to actually point out of the board. Now, that's the way we did it two-dimensionally, but if you move F tail to tail with this vector here and do R cross F, you get exactly the same thing. R cross F is providing a moment vector out of the board, just as we talked about a minute ago before. Now, this particular one's real easy. The magnitude of the moment is just R times F, because this is already 90 degrees, and we already said that the moment really only responds to the component of the force perpendicular to the moment arm. And that's what we have here. But what this principle of transmissibility is saying is that the force vector can act at any point along the line of action and produce the same moment. So what that really is saying is that the line of action is always going to be on either side of your force. The line of action is like an invisible line that goes on either side of your force on to infinity in both directions. So what it's really saying is that I can take my force vector, right now it's acting exactly at this point at R2, but I could shift it up here, or I could shift that force down here, and if I recalculate the moment, how much is it going to rotate or tend to rotate about O, I'm going to get exactly the same moment no matter where I move that force, as long as I'm only moving it along its line of action, which is either that way or this way, shifting it up and down a line in the direction of that force vector. And when you first look at that, you might say, well, how could that possibly be? We know that the moment is R cross F. But if we move the force way down here, isn't it going to produce a different moment than this one here? Well, let's take a thought experiment and figure that out. This is case number one, okay? Let's say that I move this guy way down here, okay? And I apply the exact same force. All I do is I shift it down here. So I'm going to try to draw it to scale. This guy's down here. And now basically all I did is I shifted it along its line of action down. And then this guy is R1. Okay? So the question is, does this force acting right here produce exactly the same moment as this force shifted down acting here? The answer is yes. You don't even have to think about it. You just know it's yes. Because if you have the same axis of rotation, and if you're moving the force up and down its line of action, you're always going to get the same moment about the axis. Now let me show you why that's the case. We already said that here the moment was R times F, but really what we're trying to say is it's R times the perpendicular component of F, or if you're thinking about cross products, it's R cross F, or RF sine of the angle between them. But you can see this is a 90-degree angle, so sine of 90 is 1. So it's really just r times f. So here in this location, right, in this location over here, the moment about O is r f sine theta. This is the magnitude of the cross product of r and f. We know in this case, because it's two-dimensional, that the moment's always going to come out of the board. No matter where it is, it's always going to rotate it this way. The moment's always coming out of the board. The magnitude of the moment in this case is r times f, or I should say r2 times f, times the sine of the angle between them. But we know in this case that the angle between these vectors really is 90 degrees, which really means this just drops away to 1. So really the moment's r2 times f, okay? But still, let's just leave it written exactly as it is right here, okay? Then, if we go down here, what we're saying here is that the moment produced about the same point here. In this case, it's just a cross product of two vectors. It's r1 crossed with f. r1 crossed with f, which is r1 times f times the sine of the angle between them. So the question is, if this is the moment produced by this force when it's oriented here, and if this is the moment produced by this force when it's oriented here, how do we know that these two are the same? And the answer is, I mean, we could actually put numbers to it. I could prove it to you that way, but I want you to think a little bit deeper than that, okay? What's happening here is, clearly when you look at this case and this case, the angles are not the same. In this case, the angle's 90 degrees. In this case, the angle's less than 90 degrees. So that's going to change this last term right here. So if that's the only thing that changed, if the angle changed between them, there's no way that these guys could be equal, okay? However, there's something else that changes, and it's not the force. The magnitude of the force stays the same. But notice R2 here is much shorter than R1 right here. So as you move this thing down here, what happens is the angle changes. Yes, that's true. That would change the moment. However, you also increase the length of the moment arm by a great deal. And these two things go hand in hand. So what's going to essentially happen is no matter where you move this thing up here, you're going to change the moment arm distance, and you're also going to change the angle. And when you do those two things simultaneously, what's going to end up happening is you're going to get exactly the same moment in both cases. Because when you think about it, what is the moment calculation doing? RF times sine of theta. What is it doing? You can think of it as finding the perpendicular force. You can also think of it as r sine theta, giving you the perpendicular distance to the line of action that you have here. So in other words, if we know that this angle is 90 degrees, and we know that this angle is, I don't even know, like 45 degrees, right? Then when we do R1 times the sine of 45 degrees, what's happening here from the geometry here, the sine of 45, think about what's happening. It's projecting it, and what you're doing when you take R1 times the sine of this angle, you're always getting the perpendicular, basically you're getting R2. When you do this times the sine of 45, you're getting the projection that's going to be perpendicular to this line of action. And I want to say that one more time because it's really, really important. Whenever you're doing this calculation, when you do the actual cross product, that's what I said, it's just illustrating the properties of the cross product. When you calculate this, F is the same in both cases. What you have is a different R and a different sine theta. When you calculate R1 times the sine of 45, what you're doing is you're finding the component of the distance, that's this component here, from the triangle geometry here, that just happens to also be the perpendicular distance to the line of action. So if you were to shift it up here, for instance, in some intermediate point where R was coming here and the force was located here, I would have a different angle, and when I calculated, let's call it R3 times the sine of theta, I would again be getting the perpendicular distance to the line of action. No matter where I shift this force along the line of action, when I take R times the sine of the angle, what's happening is I'm just getting the perpendicular distance, which is going to fold right on into the to the moment calculation. I hope that's clear. I've tried to make it clear, but if you don't understand exactly what I'm talking about in terms of the math here, then at least remember the principle of transmissibility and try to just remember it. And if you don't understand the proof, I'm hoping that you do, but if you don't, just remember that it's true. That basically if I'm trying to find a moment about here, it doesn't matter if I calculate it with this R at this angle, or with this R at this angle, or some other R at some other angle, as long as I'm keeping the same force and shifting it anywhere along my line of action, then I can use any point along the line of action to calculate the moment. That comes in handy when you're solving problems, because you might have a force acting in this beam, and then the way they give you the information on the problem, you might have to do a lot of work to calculate the cross product. But then you realize, oh, I can just shift this thing up and down its line of action. If I'm just trying to find the moment about O, I can shift it up and down its line of action anywhere I want, and I can simplify my calculation tremendously in many, many cases doing that. Okay. Next thing I want to talk about is very simple. By far, the hardest thing in this lesson was the transmissibility thing. I want to talk a little bit about resultant moments. Okay, so basically what happens here, whenever you have multiple forces acting on a body, and each force is causing a moment in a different orientation, which means different forces might be trying to rotate the thing in different directions. What do you think happens? Well, this is something that shouldn't come as a shock to you. Basically, we're going to add up the moments. And since every moment that you calculate really is a vector, if you're adding up the moments, you're adding up the vector quantities. You're not just adding up the magnitudes, because all of these moments have directions. So if one moment's pointing this way, meaning I'm going to be rotating about this axis, and another moment's pointing over here, meaning I'm going to be rotating about this axis, then in order to figure out how the thing's really going to rotate, I vectorially add those two moment vectors together. Maybe I figure out it's pointed that way, you know, going something like this. Okay? So the way that you symbolize that in math is the moment, which is called the resultant moment about some axis, is just equal to the sum of the individual moments that you calculate. These are the individual moments you calculate. You have different forces acting at different points from the point O, that's what this is. And basically, you know, you figure out what the resultant moment's going to be. So for instance, if I have a point here, and I may have some R, and then here I may have some F, let's call it R1 and F1, I can certainly figure out what's the moment about this point, R1 cross F1, right? But then I may also have some, let me switch colors over here. I may have another force over here that's acting F2, R2. So in other words, this force might be tending to rotate the thing this way. This force might be tending to rotate the thing this way. They're going to be fighting each other. How do you do it? Okay, well, the way you do it is you find the moment due to this one, which will give you a vector answer, which is a vector quantity, and you'll find the moment R2 cross F2 that comes about from this one, which would be another vector, and then you just add the vectors. You've been adding vectors for lots and lots of cases here. That's going to give you a resultant moment that will govern the direction in which the thing is rotating. Remember, if you know the moment's going that way, you can see the arrow. You just grab your right hand, curl it around that guy where your thumb is pointing in the direction of the moment, and that's how it's rotating. That's how it's rotating. Okay. A couple of additional notes I want to make at the end. I've said these a lot, but I wrote them down, so I want to make sure I say them again. Two-dimensional problems that are flat on a chalkboard. Even though moments really are vectors, it's very common and very easy to just do scalar calculations when you have two-dimensional problems. What I mean by scalar calculations is you know that since all the forces and the moment arms are in the page, all the moments are coming out of the page. You don't have to keep track of all the vector quantities in the z direction coming out of the page. You just do the calculations like we've done before. Keep track of rotations left versus right with plus and minus signs, and then you can basically do the problems as we've done before. But in 3D problems, I may have what I have here, forces and moments, forces and moment arms going different directions. It's going to be hard to do a scalar calculation here, so just do the cross product. This cross with this cross with this, get the two quantities, boom, add them together, get a resultant moment. Okay? And then finally, I want to make a final note on units. I don't know if I've mentioned this before, I don't think that I have, but I want to make sure you understand something. The units of moment, for instance, would be like 12, and the unit might be Newton meters, okay, because it's force times distance, perpendicular force times distance, which is the moment arm. What this is representing is representing a turning effect or a turning force. That's what a moment is, and we've talked about that many times before. Of course, the magnitude of the moment depends on how far away you are from the axis, r, and it also depends upon the magnitude of the force, F. So it depends on two things, and it depends on the angle, clearly, because it depends on the sine of the angle, which gives us that perpendicular component. But when we say something like 12 Newton meters, okay, we can also say the same turning effect as the following. 12 Newton meters is the same turning effect of 12 newtons placed 1 meter away. Okay, which means if I'm going to draw a quick picture down here, which I am, which basically means if I'm going to look down here and I'm going to have something like this, then if I have 1 meter, then the turning force or the moment is like 12 newtons. This is the force. So this might represent what I'm talking about here, 12 Newton meters, right? 12 newtons, 1 meter away, a perpendicular component of 12 newtons, 1 meter away, gives me a torque in physics is what you would call it, but a moment of 12 Newton meters. Okay, but it's also the exact same turning force as 6 newtons placed 2 meters away. Okay, make sure you understand that. So for instance, this turning of force that comes about from this is exactly the same as going 2 meters and putting half of the force here, 6 newtons. So what I'm trying to say is the turning force about the origin of 12 newtons acting 1 meter away is exactly the same as 6 newtons acting 2 meters away, which is also the same as if we go, let's say 3 meters, let's go 1 more meter, right? So let's call this 1 meter. So the total distance would be 3 meters. What do you think needs to go there? Actually, instead of putting 3 meters, let's make it nice and even. We'll make this 4 meters. So we'll take this over here and we'll bring this out twice the distance here, like this. Like this. What do you think we need to put there? Well, I need to make 12, right? So 4 times what gives me 12? 4 times 3 gives me 12. So I could cut this in half again and say 3 meters here. I just want to make sure you understand fundamentally what the concept of a moment really is. It's providing a turning effect or a turning force. If I say that 12 Newton meters is the moment or the torque about an axis, okay? That's the turning effect that you're getting there. As you know from using wrenches, if I hold my hand at the very end of the wrench, okay, and I'm going to get a certain turning force, I can get that same turning force by moving my hand to the middle of the wrench, but I got to push harder. How much harder? Twice as hard, because it's a multiplication effect. So if I'm 1 meter away, I'm going to need the full 12 newtons acting to give me that moment. If I'm 2 meters away, which is over here, 2 meters, I'm going to need 6 newtons, because 6 times 2 is 12. And if I'm 4 meters away, I'm going to need 3, I'm putting meters here, I apologize for that, 3 newtons of force. I'm going to need 3 newtons of force because 3 times 4 is going to give me 12. In all 3 of these cases, whether I'm 12 at 1 meter, 6 at 2 meters, or 3 at 4 meters, it's the exact same moment. It's the exact same turning effect or turning force. All right, I think that's about enough of this. We have talked about how to calculate the moment of a force about a axis in terms of vectors. And then what we're going to do in the next section is we're going to solve some real problems. And you will see how using vectors really saves you time instead of causing you heartburn or headaches. It actually saves you a lot of time, because when you get into 3-dimensional problems or more complicated problems, it's much easier just to cross these vectors together than it is to figure out all the perpendicular components and do all of that drawing. So follow me on to the next section and we will demonstrate that with problems. Learn anything at mathandscience.com.